In order to guarantee full understanding of this course, you should have completed previous universal molding modules: MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, MU4 Material Morphology, and MU5 Press Calculations. Your objective is to identify the needs of your process and to determine well-thought-out solutions. Because of this, before molding or making any type of adjustments to your injection molding machine, you should make certain initial calculations. These initial adjustments are known as molding from the desk. Remember that you are dealing with expensive equipment and should not rush your work. In this module, we will discuss maximum shot size, nozzle tip and sprue bushing, fountain flow effect, density and specific density, injection velocity and injection flow, barrel utilization, recovery, residence time, plasticizing position, temperature profiles, intensification ratio, maximum shot size. The maximum shot size represents the maximum amount of material that the injection unit can plastify. It is important to note that the amount able to be plasticized is greater than the amount required for the mold. We generally say that maximum recovery is greater than 30% more than is required for the mold.
Why so much? Why more than 30% of what is required?
There are many reasons, including to guarantee a cushion after the pack stage, to compensate for the compressibility of thermoplastic melt, to compensate for melt that returns to the other side of the check ring in the injection unit, etc.
What reasons or factors determine how much larger the barrel should be?
Amount of available recovery time, how easy the material is to melt, and if the material degrades or resists long residence times in the barrel. The injection unit's capacity is measured by volume, not by mass. If the injection unit size comes in mass units, for example ounces or grams, you should know that it's generally based on the density of polystyrene, which is 0.94 grams per cubic centimeter or 0.54 ounces per cubic inch. Notes: when specifying an injection unit, use volume, not mass. While calculating, you should use the specific density of your melt at its plasticizing temperature and pressure, and not that of the material at its ambient temperature and pressure. For example, the density of a polycarbonate, PC, equals 0.95 grams per cubic centimeter as a melt, 1.2 grams per cubic centimeter as a solid, and 1.04 grams per cubic centimeter plasticized.
Why does the density change, and which should I use?
Remember that thermoplastic melts can be compressed. You should use the plasticizing density, the density of the melt under plasticizing conditions. Some machine manufacturers call this plasticizing density the discharge factor. For example, a polycarbonate with a plasticizing density of 1.04 grams per cubic centimeter will be used to fill a mold with a total weight, parts and runner, of 125 grams. According to the material manufacturer, barrel utilization should be between 45 and 60%. What would be the volumetric specifications of the barrel? Injection volume required for the mold would equal weight divided by density. In this case, the injection volume required for the mold would equal 120.19 cubic centimeters. Now let's calculate the volumetric specifications of the barrel. Calculating the utilization volume of 45% gives us 267.09 cubic centimeters. This means that the barrel should be no larger than 267.09 cubic centimeters. Calculating a utilization volume of 60% gives us 200.32 cubic centimeters. So the barrel should be at least 200.32 cubic centimeters. This means that, in order to comply with the polycarbonate's requirements, the volume of the injection unit should be between 200.32 cubic centimeters and 267.09 cubic centimeters.
What density should I use if the plastic manufacturer doesn't know the density of the material when plasticized?
Unfortunately, you'll have to use a generic density, or use the density at ambient temperature and pressure. Remember that you are working with thermoplastics, materials with properties that are a function of time, temperature, and pressure. If we add to this the large number of injection unit types, we can conclude that some error will be present, even with adequate density.
Let's review.
Nozzle tip and sprue bushing. The nozzle tip is installed in the injection unit, and the sprue bushing is installed in the mold. The injection unit generates the force required to keep them coupled together. If they separate while the mold is filling, the melt could filter between them. As a general rule, think of the sprue bushing as part of the mold.
Is the sprue bushing part of the injection unit or part of the mold?
Though it is installed in the injection unit, we prefer to think of it as part of the mold. Soon you will see why. The nozzle tip is an important component. Because of this, the proper one should be selected, and it must be kept at a specified temperature. The temperature of the nozzle is more significant when working with semicrystallines rather than with amorphous materials. For example, with an amorphous material X, if the temperature is 50 degrees Fahrenheit over the required value, the tip could create a drooling effect, and strings might be seen during the expulsion of the sprue. If the temperature is 50 degrees Fahrenheit under the required value, the nozzle could get stopped up or create cold slugs that could migrate to the mold. With a semicrystalline material Y, if the temperature is only 5 degrees Fahrenheit over the required value, the nozzle could drool and strings could be seen during the expulsion of the sprue. If the temperature is only 5 degrees Fahrenheit under the required value, the nozzle could get plugged or create cold slugs that could migrate to the mold.
Where in the mold will the cold slugs end up?
They will stay in some place around the beginning of fill. Later, when we discuss the fountain flow effect, you'll understand why. Diameter of the holes and contact radius. Let's look at diameter D and radius R of the nozzle tip in the following illustration. The diameter of the bushing's opening is 1 millimeter greater than diameter D of the opening of the nozzle tip. The bushing's contact radius is 1 millimeter greater than radius R at the nozzle tip. Before you begin a universal molding lab, you should verify that the nozzle tip is properly sized. If it isn't, you must change it before starting.
What would happen if the diameter of the hole in the nozzle is larger than that of the sprue bushing?
A couple of defects could occur. One would be that excessive friction on the material by the edges could cause the melt to burn. This burned material could end up in the molded parts. Another defect seen in molds with cold runners is that the sprue stays stuck in the sprue bushing. Remember that the sprue is part of the runner and should be ejected during demolding. The solidified plastic would be shaped like the head of a rivet that would not allow the sprue to be ejected.
What would happen if the radius of the end of the nozzle tip is larger than that of the sprue bushing?
If the radius of the nozzle tip is larger, or if the end of the nozzle tip is deformed, the melt will accumulate inside the spaces and would cause the sprue to be stuck in place.
So the sprue will always get stuck whenever the coupling between the sprue bushing and the nozzle tip is mismatched?
Though that is the case much of the time, it is not the only reason. For example, sometimes it will become stuck because the interior part of the bushing was polished in a direction opposite to that of the sprue's ejection. If this is the case, talk to the mold maintenance department and review the interior finish of the bushing. Now do you understand why we prefer to say that the nozzle tip is part of the mold, even though it's installed on the injection unit? Some factories, when removing the mold for storage, also remove the nozzle tip and attach it to the mold. Nozzle Purge Program. Some processes require special nozzle cleaning programs. This is seen more with molds for rigid PVC tubing joints. This material has a tendency to be heat sensitive and will easily degrade. After each cycle, the injection unit pulls back, purging the small amount of plastic left in the nozzle. This is done in order to eliminate any material remaining from the previous cycle. This purging is used with single cavity molds, normally large connectors. With a multiple cavity mold, the degraded material will remain in the runner, fountain flow effect, and will not need this program. Never begin a universal molding lab without first installing the correct combination of sprue bushing and nozzle tip. Fountain flow effect. The fountain flow effect describes the flow of a thermoplastic melt. Thermoplastic melt is compressible, opposes movement, and wants to attach itself to the first static surface it encounters. This opposition to flowing is responsible for the fountain flow effect. Imagine melt flowing between the walls of a mold. The melt close to the metal will try to grab onto its surface and to any material already attached to that surface. The melt in contact with the cold metal will create a layer of hardened material. The melt's tendency will be to flow through the center in search of the opportunity to grab onto the first available static surface. This is the behavior responsible for the fountain flow effect that is observed at the front of the melt flow.
Does this mean that the first melt that enters the mold will stay at its entrance?
Correct. The first melt that enters the mold will stick to the first surface it encounters at the beginning of fill.
Let's review.
Density and specific density. Density is equal to weight or mass divided by volume. Specific density is equal to material density divided by water density, where water density is equal to 1 gram per cubic centimeter at ambient temperature and pressure.
Why divide by 1?
To cancel units, so that someday if you have a specific density without units, you can assume that it is in grams per cubic centimeter. Or if you would like to work with other units, find the density of water with your preferred units and multiply by the specific density. Injection velocity and injection flow. These days, it is common to see more industry personnel using universal parameters. It is also common to see newer machines provided with universal parameters, such as injection flow instead of injection velocity. Injection velocity is equal to displacement per units of time, or distance divided by time. Injection flow is equal to volume per units of time, or volume divided by time.
Why work with flow instead of velocity?
This universal parameter represents what the mold sees. For example, a cavity is a defined space or volume and is filled in a given time. From the mold's point of view, fill time and flow, volume divided by time, are also universal. Relation between injection volume, screw area, and screw diameter. Injection volume is equal to screw area times displacement. And the screw area is equal to the screw diameter squared multiplied by pi divided by 4. If we substitute in the flow equation, injection flow equals volume divided by time, where volume equals screw area times displacement, and this equals the screw diameter squared times pi divided by 4, all multiplied by displacement and then divided by time, this, at the same time, can be expressed as screw diameter squared times pi divided by 4 times injection velocity. Barrel utilization. Barrel utilization is a comparison between the maximum capacity of the injection unit and the capacity required to fill the mold. Percentage of utilization equals volume used times 100% divided by the volume capacity of the barrel, where the volume capacity of the barrel is the maximum that the screw can plasticize, and the volume used is the recovery programmed according to what is required by the mold.
So does that mean that the screw should recover to the maximum?
In a normal operation, that's not correct. If there is too much recovery, the cushion will be exaggerated. Examples: a barrel with a 35 millimeter screw with a maximum recovery volume of 134 cubic centimeters needs to plasticize 62 cubic centimeters. Given that the machine control is not universal, what would be the recovery displacement? Knowing that the screw area is equal to the screw diameter squared times pi divided by 4, substituting, the screw area is equal to 9.62 square centimeters. Also knowing that the injection volume is equal to the screw area times displacement, then displacement is equal to injection volume divided by screw area. According to this calculation, recovery displacement should be 64.4 millimeters, or 2.54 inches. How much would the percentage of utilization be? Percentage of utilization would be volume used times 100% divided by volume capacity of the barrel. According to this calculation, the percentage of utilization would equal 46%.
Are these recovery adjustment calculations reliable?
They are a reference, since the final adjustment will be affected by the temperature of the melt, back pressure, a leaky check ring, and by the time it takes the check ring to seal.
Let's review.
During recovery, the screw rotates, forcing the melt in front of the check ring and pushing the screw back. It will stop when it reaches the desired recovery position. Once the signal giving permission to inject occurs, the screw will quickly inject until it reaches the transfer position. The pack stage begins after the transfer position. This is when the melt is compacted until all the cavities are completely filled. The final position of the screw is called the cushion. Recovery. In the recovery stage, we are filling the barrel with a homogeneous melt. This normally occurs during the cooling stage. The control parameters are plasticizing time or velocity and back pressure. The recovery time should never exceed the cooling time. This applies to injection units that are not equipped with a shutoff nozzle. Back pressure could be thought of as a force that opposes free movement of the screw during recovery. As a result of increased back pressure, there is an increase in mixing, friction, plasticizing time, and material degradation. Keeping back pressure as low as possible is recommended. It should be increased only when more melting is required or if better mixing is needed. An initial or reference back pressure amount is 750 psi of plastic pressure. Remember that plastic pressure is the pressure that the melt feels.
Does the amount of plasticized material increase with an increase in back pressure?
Yes, it does. Remember that thermoplastic melts are compressible. If the back pressure is increased, a larger amount of material will be plasticized in the same volume. Plasticizing position. The plasticizing position is the place to which, during recovery, the screw should reach in order to fill the mold. This is the result of combining the cushion, the pack displacement, and the injection displacement. We could say that the plasticizing position equals the transfer position plus the injection displacement.
Why isn't the cushion considered in that equation?
It is actually considered inside the transfer position. Soon we will discuss how the transfer position is determined. Combining the equations for weight, density, and volume, we have injection displacement equals 1.27 W divided by rho times d squared, where rho is the melt's specific density, W equals the weight of the parts and runner in grams, and d is the diameter of the injection screw in centimeters.
Does this equation take into consideration the fact that the mold is filled to around 95% during injection?
Excellent observation. The answer is no. During the injection stage, some material always squeezes through to the other side of the check ring, while the ring is sealing and as a consequence of leakage between the ring and the barrel. Plasticizing velocity can be in revolutions per minute or RPM, and tangential velocity, millimeters per second, where tangential velocity equals RPM times circumference. Circumference being pi times d, with d being the diameter of the injection screw in millimeters. This is adjusted in such a way that recovery ends before the expected cooling time. Residence time. Residence time is defined as the time from which the material enters the injection unit to the time it is injected into the mold. In addition, if the mold includes hot runners, you must also consider the time that the melt resides in the manifold. Another definition is the residence volume, the maximum amount of material that resides inside the barrel.
Is the residence volume the same as the maximum plasticizing volume?
The residence volume is more than the maximizing plasticizing, since we must also consider the volume of the material located between the flights of the screw. The volume of material between the flights is more than the maximum plasticizing volume. To determine the residence time, we must calculate the volume of material, V sub r, that resides between the flights of the screw.
Isn't it complicated to determine the volume that exists between the complex geometry of the screw flights?
It could be. However, there is a simplified way to estimate V sub r. To approximate V sub r, assume that it is 40% more than the screw's maximum plasticizing capacity, V sub max. For example, how much material resides between the flights of a screw inside a 40mm barrel, which has a maximum injection capacity of 250.5 cc's. Using V sub r equals V sub max times 1.4, we find that it equals 350.7 cc's. This means that the volume of material that resides in between the screw flights is close to 351 cc's. Residence time T sub r is measured in cycles and is determined by rounding 1.4 V sub max divided by V sub required to the next whole number, where V sub max is the maximum injection volume and V sub required is the volume required by the mold.
Why round the results of the equation for T sub r to the next whole number?
Decimals are used to represent the fraction of non-injected melt that will stay in the barrel an additional cycle, and not a fraction of a cycle.
Why do we measure residence time in cycles?
Remember that we are molding from the desk, and we don't know the final duration of the cycle. Once we have completed molding and we know the optimum cycle time, we convert it into seconds. Another method that gives equal results is using the percentage of utilization. T sub r equals rounding to the next whole number of 140 divided by the percentage of utilization, which was previously defined as V sub required divided by V max times 100%. Example: a 250.5 cc barrel is used to mold two molds, one requiring 150 cc's and the other 35 cc's. What would be the residence time T sub r for each mold? Using the equation for TR and rounding to the next whole number, we find that the 150 cc mold would need 3 cycles, and the 35 cc mold would need 11 cycles. Transfer position. The transfer position is the position at which injection ends and pack begins. Remember that transfer is a screw position that corresponds to around 95% of the mold filled with compressible melt. Important data. If the transfer position is too premature, the screw could bounce and could even create short shots. If the transfer position occurs too late, the screw could reach the end of the barrel. The melt at the front of the screw is what stops the screw after the transfer position. From the barrel's point of view, the transfer position is reached when injection volume is around 95%. However, from the mold's point of view, the instant that the screw reaches the transfer position, the volume occupying space inside the mold is less than what was injected. Remember that the melt is compressible and its elastic expansion takes time. After examining dozens of processes, interviewing several molders, and reviewing manuals from various injection machines, the criteria used to determine the transfer position was obtained by experimentation. With machines smaller than 400 metric tons, if the percentage of utilization is 35% or less, transfer will be 6 millimeters or 0.25 inches. If it's between 35 and 65%, you'll need to interpolate. If it's 65% or more, transfer will be 12 millimeters or 0.5 inches. With machines larger than 400 metric tons, if the percentage of utilization is 35% or less, transfer will be 12 millimeters or 0.5 inches. Between 35 and 65%, you'll need to interpolate, and 65% or more, transfer will be 25 millimeters or 1 inch. Once transfer position is determined, it should be converted to volume. Transfer volume is equal to transfer position times area of the screw. This is also equal to transfer position times screw diameter squared times pi, all divided by 4.
Why should we convert the transfer position to volume?
Because transfer volume is a universal parameter, representing what the mold sees and is transferable to similar injection units. The change should occur in such a way that the screw's final position is greater than 0 and less than the transfer position.
What happens with defective molds that require a transfer position that is distinct from what is calculated?
If it is economically viable, repair the mold. If not, then you will have to make the necessary changes and document those changes. Example: a mold on a 500-ton press requires a fill volume of 120 cc's, and the barrel can be filled to 160 cc's. Percentage of utilization equals 120 divided by 160 times 100%, which is 75%. Given that the percentage of utilization is more than 65% and the press is more than 400 tons, the calculated transfer position would be 25 millimeters.
Let's review.
Temperature profiles. When we speak of temperature profiles, we are referring to the heat zones of the barrel. The heat zones are feed, compression, and metering. Each of these zones measures the temperature of the steel. These zones are adjusted to guarantee the most significant temperature, the temperature of the melt. The temperature profile for each material should be recommended by the material manufacturer. There are 4 basic temperature profiles: descending, ascending, lumped, and flat. The vertical coordinate indicates the deviation of the temperature, and the horizontal coordinate corresponds to the heat zones. Descending profile. The temperatures go from high to low, and this profile is recommended for materials with additives and materials that are hard to melt. It is also recommended in operations with a small residence time, percentage of utilization more than 65%. Ascending profile. The temperatures go from low to high, and this profile is normally used in situations where the residence time is extremely high, percentage of utilization less than 30%, so that it avoids premature or extensive heating of the material. Lumped profile. The initial temperature is low, rises considerably in the compression zone, and lowers in the metering zone. This profile, though little used, is suggested for materials without additives for which the residence time used is moderately high, percentage of utilization from 40 to 65%. Flat profile. In this profile, all the temperatures are the same. This could be used with materials with no filling or additives in which the residence time is moderate. Remember that this is a reference. Consult your resin supplier for the most adequate profile for your material. Another reference for information could be the screw and barrel supplier. For example, it is common to use barrier screws with highly semicrystalline materials. A descending profile would be recommended in this case.
Why do resin manufacturers provide temperature ranges for each heat zone of the barrel?
There is such a variety of types and sizes of screws that most of the manufacturers are obliged to provide minimum and maximum temperature ranges for each heat zone.
With what temperature should we start our process?
It depends on various factors, such as the type of material and the residence time. We use the barrel's percentage of utilization as our significant variable. If the percentage of utilization is excessively high, we will use the upper temperature limit. Inversely, if the percentage of utilization is small, we would use the lower temperature limit. Consider using the following table, where the temperature by zone is dependent upon the percentage of usage. Adjust to the zone's upper temperature limit if the percentage of usage is equal to or greater than 65%. Adjust to the zone's lower temperature limit if the percentage of usage is equal to or less than 35%, and interpolate if the percentage of usage is between 35 and 65%. Again, if the percentage is equal to or less than 35%, use the lower temperatures of each range. If the percentage is equal to or more than 65%, use the upper temperatures of each range. If the percentage is between 35% and 65%, interpolate. Notes: the thermocouples in the barrel's temperature zones read the temperature of the metal. The most significant temperature is the melt temperature. Verify the temperatures with the resin supplier or the screw and barrel manufacturer. Intensification ratio. It is imperative that we understand the relation between hydraulic pressure and plastic pressure. The plastic pressure is intensified close to 10 times the hydraulic pressure. The intensification ratio, R sub I, represents the relationship between hydraulic pressure, P sub H, and plastic pressure, P sub P. Other definitions are: the intensification ratio is equal to the plastic pressure divided by hydraulic pressure. This is also equal to the area of the hydraulic piston divided by the area of the injection barrel, and is also equal to the diameter of the hydraulic piston divided by the diameter of the injection barrel.
Let's review.
Important. Before molding or making any adjustments to the injection machine, you should do some initial calculations. Remember not to rush your work. Do your initial molding from your desk.